Right. So this graph, these are three graphs over the top of one another. The y-axis, it says absorption. So it's how well something is absorbing that particular light. So over here, the x-axis is the wavelength of that light. Okay, it's only going to be between 400 and 700 nanometers, which is a very small chunk of the different types of electromagnetic waves out there. If we zoom out for a moment, you can see that it's part of the visible light spectrum, the part of the electromagnetic spectrum which we call visible light because we can see it. But it's actually a tiny, tiny, tiny slither of all the different electromagnetic waves out there. And what it's saying is that there are different cells in our eyes and in our retina, basically the detecting part of our eye, that respond differently to different wavelengths of light. So we have, and they're called cone cells. There are rod cells as well. Rod cells pretty much detect everything, more or less, within this range. But then cone cells are much more specific to certain wavelengths. So we've got our blue cone cell, which is very, very good at detecting this particular range, 445 nanometers. And it's fairly good at detecting the wavelengths around it. And the same with this green one here. We call it the green cone. It's really good at detecting a wavelength looks like 535, and red 575. So obviously it's called a blue cone, a green cone, and a red cone is because 445 nanometers is blue, 535 nanometers is green, and 575 nanometers, well, it's just, according to this, it's just not quite red, but getting on for red. It should be, so you could call it an orange cone, really. So if we see blue light, then our blue cone, our so-called blue cone, gets loads and loads of activity. It absorbs a lot of light. The green cone absorbs a little bit, but the blue one absorbs lots. So just to demonstrate exactly how I'm working that out, I'll just draw a dotted line. So this would be my blue light being shined, like a blue laser maybe. And you can see a little bit of the green cone is detecting light, but loads of the blue cone is detecting light. And so my brain goes, you're looking at blue right now, because the blue cones are firing, a little bit of green, but mostly it's blue, so it's obviously blue light. Likewise, if I look at green light, then my green cone fires, and now again I get a tiny bit of the blue and I get a fair bit of the red cone firing, but again my brain is used to all that and it goes, yeah, I expected all that. This is clearly green light you're looking at. Now this one here looks like it's not actually red, is it? More like orange. But so if I shine orange light, then my red cone detects a bunch of stuff. In fact, it seems to be my red cone's favourite colour. But my green cone actually detects a fair amount as well. If I shift to the right and I shine red light, now I still get a fair amount of my red cone, but not much of my green cone. And this is pretty much why we call this cone over here a red cone rather than an orange cone. Anyway, so how do we see yellow light then, for example? Well, if I shine yellow light, we can see that what's going to happen is I get roughly equal amounts of the green cone and the red cone. So even though I don't have a specialized yellow cone, then two of my cones are detecting light at the same time. The same with cyan. If I shine cyan light, just like a sort of sky blue, the blue and the green cone both detect light at the same time. And you can say any other colour. So we could say, whatever colour this would be down here. My cones expect a certain activity, a tiny amount in the red, a medium amount in the green, a fairly large amount in the blue. And then it would know it's looking at this colour here, whatever it would be. And it's called itself purplish blue. So you can trick your eyes here because so computer monitors and TVs save a lot of money by using what they understand about the eyes here, and thinking, well, rather than getting pure yellow light, we'll just, because the way we see yellow light is by our green cones and our red cones detecting it. Why don't we just shine a little bit of green, a little bit of red, so as we'll see this much activity, and our brain will just think it's yellow anyway. And they try it out. That's exactly what happens. This yellow square you're looking at right now, this yellow rectangle, there's no yellow light coming out of it. It's only green and red. It doesn't look like green and red, of course, but that is what's happening. So if you look closely at your computer monitor, they look like this. Just these three different colours. And you'll notice, you might, if you looked at it, looked at some of the, you start studying this topic, you'll see RGB coming up all the time, and that just means red, green, blue. So RGB LEDs, red, green, blue LEDs, light emitting diodes. So that's basically how we see colour. Now we've got a colour chart here. Actually, I'm going to you can go to this animation and get the colour chart, but I'll get one now as an image, and I'll put it right there. Right. So first of all, if you look at this one, this is the one that we're more used to. If you ask most people on the street what happens when you mix red and yellow, they'll say it makes orange, right? Blue and yellow makes green. Blue and red makes sort of purpley colour. And if you mix them all together, they make a sort of brown colour. Like if you played with crayons when you were young, you just crayon loads of stuff all over your paper, and you're like, oh, it's just all brown. Well, that's with paint and with like crayons and stuff. It's a slight. There is a way how these connect, but we're not going to go into that right now. Essentially, that's a Venn diagram we've got there of how they mix with paint, whereas with light it does this. So it's a bit confusing at first, but what it's saying is if I get red and green light, I make yellow light. If I make green and blue light, I get cyan. Blue and red, I make magenta. And if I mix them all, it makes white light. So it seems a bit weird because we always think of white as being nothing. Like you start off with a plain white sheet of paper and there's no paint on it. So it seems a bit odd to think if I cover this in colour, it's going to make white light. It feels like it would do the exact opposite. But again, that's when you mix with paint, not with light. So a good way to think about how this would make more sense is if you think the more light I get, the brighter it would be, and the brightest colour there is white. So clearly mixing all the colours would make white. So we can mix colours, mix light colours to produce that. But that's because of how the cones and rods are working inside our eyes.